Okay, so today, again, you're going to take your Module 3 exam starting at 2:15. You have 24 hours to do that. You also have the last, wait. I'm trying to think about what today's quiz is. I might have effed up. I honestly can't remember if today's quiz was on Module 3 stuff or Module 4 stuff. I don't remember. I'll have to check when I get back to my office to verify what today's quiz was on. But you definitely do have that exam that's opening today. But we're going to start Module 4, and really, I don't know why I scheduled so many lectures for it, but it's one chapter. But within that one chapter are a lot of reactions, and the next slide will sort of generalize what they are. But really it's the chemistry of the alpha carbon. And so we're talking specifically about these oxidation state 2 or 3 functional groups. And then we're going to use the reactivity profile of the carbonyl that helps us deprotonate a CH bond at the alpha position. And then the context of this is it's really how we form carbon-carbon bonds. And then it can be generalized into how it's done in your body and how nature does it. So I think either Monday or Wednesday of next week, we'll talk about how like plants or marine sponges make molecules that are pretty complex and actually have been shown to have anti-cancer properties. And so we'll talk about bond disconnections, relationships of oxidation states, and then, we can wonder why a plant is producing this crazy complex molecule when it actually doesn't do anything really for the plant other than maybe a defense mechanism. So the big picture of this module is that we're learning how to make reactions originating from the alpha carbon. And we spent the last couple modules talking about oxidation state 2 and 3 functional groups. So we can see with oxidation state 2, X is either H or carbon, so that's aldehyde or ketone. And again, ketones are going to be the one that is going to cause us the most trouble in the sense that there we can have 2 alpha carbons. Acids, esters, or amides are at oxidation state 3, and those would only have 1 alpha carbon because that X group is a heteroatom. So again, what's special about the alpha carbon is the pKa is significantly lower than your typical sp3 hybridized carbon H bond. So depending on what the functional group is, it's about 20 to 25. Your normal CH bond is about 45 to 50. So on the log scale, these are about 10 to the 25 times more acidic. In terms of the rest of the chain, you just follow the Greek alphabet, so beta, gamma. It's nice to know those things when we're just talking about in terms of like following a path. Let's say, okay, look at the beta carbon, and then you sort of know where to bring your eye to. So because these are significantly more acidic, if you have a base that will abstract it, it's going to generate a carbon anion, so a carbanion at the alpha position. You'll you'll typically have, that will be balanced off by some metal M. But this can have a resonance form where that lone pair is now delocalized onto the oxygen, and that can help explain the increased acidity. The structure shown in the bottom resonance form is called an enolate. So that comes from alkene, and then this is an alkoxide. In things that end in ATE in chemistry are typically negatively charged. So an enolate, that's the reactive intermediate. In the squiggly line, is basically you can have cis or trans geometry, so geometrical isomers of that beta carbon relative to the oxygen or the X group. So an enolate is going to act as a nucleophile. And then as you see in the reaction proceeding, depending on what electrophile you add, the name of the reaction is different. So that's, as I said, this chapter has a lot of reactions in it. So we'll talk about alkylation, aldol, and Claisen. And what I've highlighted under the arrow with the red number, that's the oxidation state. And so that's going to be your beta prime. So I'm going to use that prime to show that it's now branching off from the original carbon chain of what you started with. The take-home message for all of these is that you're always forming a bond between the alpha carbon and the beta prime carbon. So when you look at the oxidation state of the products, see how it's one lower? So that beta prime has always been reduced. So alkylation is your typical SN2 reaction. So that has to follow that trend we learned in terms of electrophile reactivity. And so you end up with a beta prime that's at oxidation state 0. The aldol, that's a combination of two words, aldehyde and alcohol. And so notice now the leaving group doesn't really leave the molecule. The leaving group is the pi bond. So that oxidation state reduces from 2 to 1. And so these are typically beta hydroxy. And then depending on what X is, if X was an H, you would say it's a beta hydroxyaldehyde. And the last one, Claisen, that's actually named after a organic chemist. And this chapter is full of these sort of names. So when I say Claisen, unless you sort of read about it or understand it, you wouldn't know what are the functional groups present in the product. So a Claisen uses an oxidation state 3. And as we learned in the prior module, this OR group, it's being substituted. So it's a nucleophilic acyl substitution. And so the rest of that OR3 group is whatever's in your enolate. And so now you have a beta keto. And that can be aldehyde, ketone, ester, whatever you started with from your enolate. So this is a pretty influential chapter as I said, because we're learning how to make carbon-carbon bonds, and then based on the electrophile, we're controlling the oxidation state. The other significant thing to mention that's not pointed out here is that alpha carbon will generally become a stereogenic center in the product. And so that introduces a whole nother level of complexity about what you're producing, and can you favor one stereo center over the other. But to just preface that, I would say in general, so the decade I was born, probably 3 or 4 decades before you were born, in the 1970s, the aldol was really the reaction that catalyzed a huge transformation in organic chemistry. Because I said you're producing a stereo center, and people wanted to learn how to control that. Even if, the goal of any reaction is to produce one thing in 100% yield. So by one thing, I might mean one stereo center, not 100% of a mixture of R and S. You only want R or S. And so people began to investigate that and how they could control everything you see here. What is X? What base you're using? What's the nature of the electrophile? And so all of those things catalyzed a huge jump in organic chemistry as we know it. So we'll look at these different oxidation states as a review, and then talk about the complicating factors. So as we pointed out, the presence of the carbonyl increases the alpha carbon acidity. The beta, the gamma, delta, going down the chain, that's your normal sort of pK of 45 to 50, so we're not worried about those. So we have aldehydes, ketones, esters, amides, and then acids. So aldehyde, ester, amide, acids, again, those only have the one alpha carbon. The ketone is the pain in the butt here, because as I highlighted in blue just now, that alpha prime carbon. So when you're treating with a base, which alpha carbon is going to get deprotonated? Because those will generate different enolates. And so just to write some numbers down, if you look at the ratios, so alpha equals 2 hydrogens, alpha prime equals 3. So overall we have 5 total alpha hydrogens. So this would be what? 40%, 60%. So there's the statistics of it. Just based on that, you would expect, well, the one with more hydrogen should react more often. But now everything we learned up into this point, from organic 1 to organic 2, the nature of the base that you use can either favor the statistic, so you can bump that 60 up, or you can reverse it completely, where it just goes after the CH2 and not the CH3. So just again, to put it in perspective, we are talking about sp3 hybridized carbon, which normally has the pK of 50, but it's significantly lower. It's almost approximately the same as what you see with an alkyne. So again, sp3, and then the pK is 20 to 25, again, depending on what X is. So for now, let's just consider, these cases of X where we only have the one alpha carbon. And so now you have two hydrogens. And as I said, that's how you form the carbanion. And then it has these resonance hybrids, which we call the enolate. And so here's the cis or trans geometry. So normally with these, we're going to use E or Z. And the way you figure that out, so in blue, I'll highlight each sp2 hybridized carbon of the alkene. And then in green, I'll show you the priority. So you just use like the SIP stereochemical nomenclature where you use atomic number. So oxygen versus X, say if X was H, oxygen would be priority 1. So priority 1, that would be priority 2. And then on the other one, we have hydrogen, that's priority 2, and then carbon's priority 1. Since the ones are on the same side, that would be cis, but it's preferred to use Z. Then for the E, since the ones are opposite, that's trans, or E. So I can't stress this enough. All these little details matter ultimately in how these reactions proceed and what the stereochemistry at the alpha position will ultimately be. So the negatively charged species are called enolates. And if they're neutral, if the oxygen has an OH, then it's called an enol. So an example of that would be so that's an alkene alcohol, an enol. It's just been abbreviated and smashed together. So you can run these reactions under acidic or basic media. So acidic, again, is going to be enol. Basic will be enolate. And the variables are whether you're starting with the aldehyde or ketone, or ester, amide, any other oxidation state 3 functional group. The number of alpha versus alpha prime hydrogens. And this will be a key one here, the nature of the base that is used. acidic basic conditions, the geometrical isomer, so again, the base will help determine which one of those is favored. And then ultimately the electrophile, whether it's going to go alkylation, aldol, or Claisen. And let me just further highlight you're looking at the beta prime oxidation state to determine that. So we'll run through just some questions about this ketone, butanone, and start to see how things can get pretty complex as we answer these questions. So how many alpha carbons does it have? Again, here's the carbonyl. And we're just looking at the carbons right next door. So we have alpha and alpha prime. So we have 2. It says, are they equivalent? So the answer is no, because I immediately called that one alpha prime. If you had this ketone, alpha and alpha, they would be the same. So this is symmetric, and then this is non-symmetric. So really, in this, the non-symmetric case is where you're going to run into, the most questions of figuring things out. So the ratio here is 3 to 2. And to state that another way, that's a methyl group. This is a methylene group. And so if we continue over here, beta prime, I'm just going to write this note. Those are not acidic, because there's no stabilization due to resonance. So if you take butanone plus this base, so again, that makes that the acid. And I'll talk about why the arrow is drawn the way it is. It's asking you how many discrete sodium enolates can you form. So again, sodium's plus, oxygen's minus. So at the alpha carbon, you have 3 hydrogens. You remove one, you still have 2 hydrogens. So you do not get any cis or trans geometry of that double bond. So that carbon, since they're both H, and H, even if you drew it the other way, you'd still get the same thing. with alpha prime. You would get two different enolates. So if we assign priority, oxygen versus carbon, so oxygen would win there. Carbon versus hydrogen, carbon would win. They're on the same side, so that would be Z. And then the other one would have to be E. And so the arrow is drawn that way because the conjugate acid that you get after you deprotonate is ethanol. So that has a pK of around 16. These alpha hydrogens have a pK of, around 20. That difference is less than 5. And so really, the way to think about it chemically, if you take the butanone, sodium hydroxide, your reaction flask is going to have 1, 2, 3, 4, 5, 6 things in there all at once. And so the equilibrium means, well, because this acidity isn't so great, this can act as a base, that as the acid, and it goes back this way. And since you have 6 things in there, milling about, when you add in the electrophile, now how do you choose which one is it going to react with? And so that's going to give you a mixture which you do not want to deal with. So we'll talk about controlling this arrow with the nature of what this base is, so that this and this react, they're fully consumed, and it only goes to the enolate. This was one of those questions where students would provide a sequence of digits that correspond to the arrows. And in theory, since this is your base, the arrow would have to start at 8. So we want to form the least substituted. So 8 to 6. And then the next arrow would be 3 to 4. So when I say least substituted, really what you're counting is the number of carbon substituents to the double bond. So any enolate is going to have the oxygen. So we have 1 carbon substituent. If we deprotonated from the other alpha carbon, now you would have more, so you'd have 2. So that's another thing to consider, is the substitution pattern of the alkene that's generated. So for the more substituted, we would have 8 to 0, 5 to 2. So I would say these are di-substituted. And then we're going to use that information to talk about thermodynamic versus kinetic enolates. So thermodynamics deals with stability, kinetics deals with rate. And so here they are all in one slide. Something you'll want to commit to memory. The kinetic enolate is less substituted. And that will come from the alpha carbon that has more hydrogens. The thermodynamic enolate is more substituted, and that comes from the alpha carbon that has the least amount of hydrogens. So as we progress through, this slide deck, this module, what we want to think about is, can we use different solvents and different bases to favor one of those specifically? So just as a review here about assigning E versus Z. Again, you're using the SIP rules, which are based on atomic number. So you look at the carbons of the alkene as highlighted in blue, and then the two substituents bonded to each. The directly attached atoms, you're using the atomic number to then assign priority. So the ones here are on the same face, so that gets Z. Here, they're opposite, so that gets E. And I have some slides probably 2 weeks from now. If I can go on a smidge of a tangent, just to give you why I think this is kind of fascinating, and I think you'll be able to understand based on everything you know. If you look at that alpha carbon in particular, and we do a test, if you substitute one of these out for something different, that makes that alpha carbon a stereocenter, right? And so what that's telling you is, even though these H's are bonded to that same carbon, the hydrogens are called prochiral. Even though they're not chiral now, they're prochiral in the sense that once one gets gone and you substitute it, now you've generated a stereocenter. And so to further, explain to you that wedge means it's coming out towards you, right? And the dash is behind. So that's a spatial orientation. And if I do a bond rotation, and I'll highlight it in different colors here. So we'll say that's green. If we rotate, that green one is now here. This yellow one is now in front. So those are the things that people started to think about, on the molecular level, is how do we control that so we can go after the green or the yellow hydrogen. And maybe what's that movie with Alec Baldwin? Malice. He's like a heart surgeon. He's like, I am God. So it's like humans trying to control what's happening in that flask using the parameters that they can. So on what we know now in your textbooks, like we can control this stuff to get, only one product. Which does mimic nature, which is, over the however many years you believe the world has existed, thousands or billions, evolved to the point where nature has figured all of this stuff out, but nature uses enzymes to do it. So when I first made these notes, this was when, do you know who Meghan Trainor is, or have you aged out of her? I'm definitely aged out of that, but she had a song all about that base. So the nature of the base that you use will help you control what enolate you form. And so another base that's commonly used is called sodium hydride. Even though the word hydride, which we think of like adding to carbonyls to reduce them, this is typically employed as a base. So Na plus and then H minus. So that's a much stronger base than the alkoxide bases. So for example, plus and then minus, even though I'm showing this as a covalent bond here in the middle, the hydride owns those electrons. So that would generate the kinetic enolate, and then you end up forming H2, which is a gas. And the pK of that, I think is about 40. So if you're starting from a pK of, we'll just say 20, the difference now is approximately 10 to the 20. Or sorry, the difference is 20. And the difference in acidity is 10 to the 20. And that's why we can use, that arrow, which is telling you that the ketone and the base are all consumed. You no longer have that in the reaction. You just have your enolates. And so now we sort of narrowed down the conundrum of too much stuff in the flask. We're now zooming in on one thing in particular. So the kinetic enolate comes from the alpha carbon with more hydrogens, and it gives the least substituted alkene. The thermodynamic enolate comes from the alpha carbon with fewer hydrogens, and it's more substituted. And what, again, we're funneling in here on is how can we choose a base that's going to favor one over the other? So that's in the presence of an external base, but anything with a carbonyl will have a natural equilibrium to it under neutral conditions. And so that equilibrium is called the keto enol equilibrium. If you're starting with like an ester, I think it's still called keto, even though that sort of brings the word ketone into your mind. And really it's the difference between the carbonyl versus the alkene that's present. So again, these neutral forms are called enol forms. And what it is just a migration of an alpha hydrogen, so say 1, 2, 3. So those will naturally be present. Like if you had a bottle of butanone, you would have some of those enols in there, say maybe 0.5% or something. The ketone or the carbonyl form is preferred just based on bond association energies. The carbonyl is a much stronger bond than the alkene, and then you can do the rest of the sort of math to figure out why that percentage is preferred. So one other key word here. Again, since these are isomers, the word that's used is tautomer. And I could be wrong, but I think for the purposes of this class, the tautomer is just the location of that hydrogen atom. It's either on the oxygen or it's on the carbon. So to help us sort of ferret out all these little details, what I said about like a test reaction where you're substituting H for something else. So H, D, and T. So hydrogen, deuterium, and tritium, those are all isotopes of hydrogen. So hydrogen, as we know from proton NMR, is present in about 99.1%. Deuterium is the next heaviest isotope, sort of present trace amount, and then tritium is the radioactive one. So what are the implications of running a reaction with a deuterated base or deuterated solvent in relation to how the carbon hybridization changes? So NaOD, that's just the deuterated version of sodium hydroxide. And then D2O is called heavy water. And so if you're ever on Twitter or Reddit, Twitter is a little bit more PC. Reddit, you get into like, not the dark web, but people will ask, can you drink heavy water instead of like water? Will you die? That sort of thing. But D2O, it's commercially available now, primarily due to the development of nuclear weapons during World War II. They use D2O in these reactors, basically, and it's sort of a byproduct of that process. But basically, so there's your base, D2O is your solvent. And just for question number 1, say we were starting with acetone, and we treated that with NaOD and D2O. Those things look the same. Sodium hydroxide, sodium deuteroxide look the same. It's not like purple because of the deuterium or anything like that. So if you took acetone and those two things, what would happen? The base is going to abstract those alpha hydrogens, generate an enolate that's going to get a deuterium from the D2O. So it'll happen stepwise. So I'll draw a 1 and then I'll sort of extrapolate. So you have a symmetric ketone. So you have a total of 6 alpha hydrogens. So we have C3H6O. The base will abstract. The enolate gets deuterated. So now we would have this. So now we have C3H6O. H5DO. And eventually, if you let it go long enough to a certain point, all of them will get exchanged. But remember, this is equilibrium, so you'll have a mixture of these things. You would end up with C3D6O. And one reason why this is useful is, so if the atomic masses of these are 1, 2, and 3, the C3H5DO, it's going to be 1 mass unit heavier than C3H6O. And then your D6 is going to be 6 mass units heavier. Chemically, they'll still have pretty much the same properties. There's another area of study if you're interested called kinetic isotope effects. And that's what chemists use to really probe mechanisms. If you do go into biochemistry or cellular and molecular biology, the stable isotope like deuterium and the radioisotope tritium, that's what people used in the 40s, 50s, and 60s and so on to study enzymatic reactions. So, like for example, you can stick a deuterium at a specific place in a molecule. You let the enzyme do its thing, and then you say, okay, is that deuterium still there or is it gone? And that's all, again, measured through mass spec. So the second question, I think I'm going to conveniently ignore for now until we get a little bit later on where we learn a little bit more stuff. So what about the same line of reasoning? If you start with cyclopentanone, you do the same thing. What is the molecular formula of the product? So we're starting with C5H8O. How many alpha hydrogens are there? Hydrogens. 4. So that's telling you that 4 of them have to be replaced. So you would end up with C5H4D4O. So is anyone going to study pharmacology or toxicology or anything like that in their future? No hands up. Again, just as a brief aside, one of the reasons this is useful again is when a prescription drug is undergoing its clinical testing, they'll do these tests where the pill will have, I'll call this unlabeled, and then this labeled. So the pill will have a mixture of those things, and as I said, for the most part, they'll behave chemically and physically the same. So when the pill is taken with a healthy patient, then it's excreted. We'll just say through urine. The urine is then analyzed for the drug and then metabolites. So if you're trying to identify, say, a metabolite, how the drug's been changed, you can look at the product distributions by mass spec to see, okay, we're expecting, it should be 4. We're expecting 4 deuteriums in there, but we only see 3 now. And so what that's telling you is, okay, at that site, a metabolism has happened. So through this sort of rational design of chemical reactivity, you can sort of then back infer about how things are being transformed in the liver. And a major issue with I sort of think is the human body is like a giant reaction flask. Like if I'm drinking Coke, it's getting metabolized into things, right? And then it comes out. So when you take a prescription drug, the drug does its thing and it's the drug, but then the liver is making metabolites. And those are other things, right? And so is that doing then other things that you don't want it to do? So a lot of the FDA screening is regarding the toxicity of metabolites. Say this drug is like the best thing to treat brain cancer, but then it produces this metabolite that's going to kill you. And so then it can't be used. So there's, from the science that you learn in all these classes, that's what is applied and studied in a lot of companies. So for this one, we end up with B. And then again, just to keep in mind, nothing is happening at the beta position. So we ended up with C5H4D4O, and we want to treat that with MCPBA, which is something we learned in Module 3, and it's asking you what that product will be. So a ketone plus MCPBA will do a Baeyer-Villiger reaction. And do you remember what the name of the product will be for that? You start with a ketone, you end up with, so this will be a lactone because it's cyclic. So a lactone, so that's a cyclic ester. And so based on that information, which product do you think will form? So B is your ester. Since it's cyclic, it's a lactone. And again, what the MCPBA is doing is just inserting an oxygen between the carbonyl and the alpha carbon. And so what's cool about this is in your starting material, see that symmetry? Now what you've done in the product, you've transformed one of those alpha carbons into a delta carbon, and you've moved those deuteriums sufficiently far away from one another that it's at a completely different site. And so as I talked about metabolism, if you had a suspicion that, okay, yeah, we think something's happening here, you would be able to tell that one of those deuteriums is going away. So that's the sort of state of the art in which how these things can be analyzed. And so now this was the question I wanted to return to about stereochemistry. We're going to start with a ketone. It has two alpha carbons, alpha and alpha prime. Alpha prime, you'll notice, is it's sp2 hybridized, and it has no hydrogens. So we would say that's non-enolizable. So we don't even have to worry about it. Alpha prime has one hydrogen, and that carbon has 4 unique groups, which make it the S stereochemistry. So under these conditions, if we treat with sodium ethoxide in ethanol, basically what we're trying to answer is, how do we know anything happens? The sodium ethoxide will deprotonate the alpha hydrogen. That then becomes an enolate. And what's important about that is that alpha carbon now is sp2 hybridized, which means it's achiral. So when this then collapses to react with ethanol, it's going to reprotonate, but it can do it from either face of that enolate. So you're going to end up with a racemic mixture of R and S. So you're reforming your S, but you're also getting an equal mixture of the R. And so if you took that mixture and you put it in a polarimeter, the specific rotation alpha would equal 0. And so that experiment helps us understand that, yeah, the alpha carbon is more acidic. It's proceeding through an achiral intermediate, and therefore we have to generate a racemic mixture. So again, why would that be important? Say Pfizer is developing this drug where the alpha carbon is a stereocenter, but then it's taken and then it's metabolized to form this racemic thing there. And maybe the only activity came from the S enantiomer, and the R is either inactive or it's toxic. And so that would be an issue. One, because right away you're losing 50% of the activity, but then if there's this toxicity issue, that will just kill the project. So for this question, again, the enolate is achiral. That's the important thing. If I can do a little art here just to verify that. So there's the alkene with the phenyl and the methyl group pointed out towards you, the oxygen and the ethyl group going away. So if my phone is the enolate, you're sort of looking at the edge of the alkene. So when it collapses, the proton can come from the top or the bottom equally. There's nothing that says it can't. And that gives you the 1-to-1 mixture. Any questions at this point? So we've seen two bases so far, sodium ethoxide in ethanol. So that's typically the pair. Like any alcohol you can make a base out of. The other one we saw was sodium hydride. And now this next one, again, which sort of gained a lot of popularity in the 70s and 80s, is called lithium diisopropyl amide, or LDA. So that's pretty much how I'll refer to it as LDA. And it is a very strong base. And something to keep in the back of your mind, acid base is all about proton transfer. But then as we learned in Organic 1, when things are negatively charged, they can also be nucleophiles. So the way that this base became the most popular is you're starting with diisopropyl amine. And so there's the isopropyl groups. And on the page, they look sort of small, but in reality, those isopropyl groups are pretty big. So it's a bulky base. That makes it a really bad nucleophile. So starting with the amine as the acid, we use this other base called butyl lithium. And so the lithium's plus, the carbon is minus. That will abstract that hydrogen. And then we get the LDA. And then the conjugate acid is butane, which is a gas, and that will just bubble out of the solution. Because these bases are so strong, notice the solvent now. The solvent is an ether, and all of the hydrogens in that have a pK of about 50. So there should be no interactions with that solvent going on. And the reaction is pretty exothermic, so that's why it's run at minus 78. That's a common temperature for organic chemists because that comes from taking dry ice, so solid carbon dioxide, and then you add it to acetone, which is that ketone, and it forms a nice slush. And so you can get to minus 78. Like if you just ran this with ice water, you could probably do that, but it's probably a little bit too exothermic. You might see some popping going on in the flask because acid-base reactions, as we said, are the fastest. Like as soon as the base is added, the party starts. It's not like 3 hours later they get together and react. And so that external bath helps control that temperature increase of the reaction. So now we'll look at controlling which alpha carbon gets deprotonated based on the base that we're using. So we're starting here with 2-methyl cyclohexanone. And notice that this has an alpha hydrogen, which is CH2, and then alpha prime with it, which is just CH. So if we use LDA as the base, that's preferentially going to form the less substituted enolate. So that's the kinetic enolate. The reason for that LDA is very reactive. And so it says, okay, I see two of these in preference to one of those. I see that, I'm going to go after that, then I'm going to form the kinetic enolate. The thermodynamic or more substituted enolate can be generating using sodium hydride. Now, one thing I want to point out, you generate LDA in THF through that prior reaction on that slide. Sodium hydride itself, like in its purest form, is sort of a off-white solid, but most of the time when you buy it, it has like a dull gray color to it, but it's a solid. Like it's an inorganic solid. So when you add it to sodium hydride, it does not go into solution. It forms like a suspension. And so if you can imagine that solid surrounded by liquid, it's only slowly going into solution. So it's not all in there at once. And because of that, it's more selective in what alpha hydrogen it's going after. It's like, well, it took me forever to get into solution. I'm a little bit more picky about things. So now I can form the more substituted or thermodynamic enolate. And through those sort of physical properties, we've now been able to differentiate alpha from alpha prime with a non-symmetric ketone. So another way of controlling where the action happens, and this is more substrate-based or starting material, is looking at systems where you're completely blocking one side of the carbonyl. And these are the non-enolizable. So in the first example, you've blocked that alpha prime with methyl groups. So nothing can happen there because there's no CHs. The second example is just another sort of cheap example. I've taken two of the methyl groups and tied them into a ring. And then the last example, the carbon is now sp2 hybridized, but it's part of a benzene ring. And so as I said, as humans, we want to control the environment, control the situation, and this is a way of doing that. So we're saying, okay, it can only react here, and I don't have to deal with all of these other issues. So now that we have a good preparation of things, let's look at the alkylation reaction. So that was the top one on the first slide. We're going to use sodium hydride and THF to generate the enolate, and then we're going to add ethyl iodide. So ethyl iodide is the electrophile. That carbon is at oxidation state 1. The alkylation is going to do a reduction, so that beta carbon is at oxidation state 0. And so by looking at these, can you eliminate one of them immediately? Any Texans in the crowd? Anyone from Texas? Got one. So one of these has a Texas carbon. So So that's sort of what every organic chemist learned. Everything's big in Texas, or the Texas star, I guess. So this carbon has 5 bonds. So since everything's big in Texas, 5 is more than 4, so it's bigger than normal. Plus, it's happened at a carbon that has no hydrogens to substitute, right? The next biggest distractor is C, because C has done a nucleophilic addition to the carbonyl, and we're not interested in that. So we want the action to happen at one of these H's of that alpha carbon. So one of them needs to get substituted, and then the electrophile has 2 carbons. Choice A only has 1, so D is going to be the right answer. So let me draw some stuff on that, and then I'll go back and draw the intermediate. So here's your alpha carbon. This is the bond we just made. And that beta carbon, or if we want to say just beta prime, that's coming from the electrophile. So the sodium hydride forms this. That's your enolate. This then collapses. So that's your SN2 reaction. So your alpha carbon's always there, and then we're adding 2 more. So the new bond and then the extra carbon. So I think we'll leave it at that for today. But basically the take-home message is anytime you see a carbonyl, look to the alpha positions, see what the oxidation state is at the beta, and that's going to tell you how you can make that bond. And then on Monday, we'll look at other reactions at the alpha carbon, and then how we can use those in increasing the complexity. So your Module 3 exam will open in 1 minute and 45 seconds. I have to check on the quiz for today because I do not remember what it was on, but I'll send a Canvas announcement once I verify that.